So today is the 5th of May. So we will look into slide number 64, lead compensation. Okay. So this is the third compensator in the frequency domain design. Okay. The first one is the gain adjustment. The second one is the lag compensator, and the third one is the lead compensator. Okay. So lead compensator is used to improve the transient response. Okay. So for lag compensator is used to improve the steady state error, and lead compensator is used to improve the transient response. So its function is similar to the PD control. Okay. So you can see here with the board diagram, okay, the lead compensator will increase the phase margin, okay, and reduce the overshoot percentage, okay, and at the same time it will increase the gain crossover frequency and bandwidth to realize a faster uh, transient response, okay. So the formula for lead compensator is shown here. Okay, sorry. Where you have a G lead. Okay. Okay. G lead. Lead meaning leading. Okay. So it's equal to 1 over beta uh, S plus 1 over T. Okay. Over S plus 1 over beta T. So 1 over beta actually is the constant that will multiply the transfer function of the lead compensator. Okay. But this form is difficult to remember. Okay. So we simplify it. Simplify. So it becomes GC equal to S over ZC plus 1. Okay. And over S plus PC plus 1. So ZC is the zeros. And PC is the pole. Okay. In lead compensator, ZC is less than PC. Okay, this is for lead. But for lag compensator, last week, ZC is greater than PC. Okay, it's greater than PC. So in lead compensator, okay, there is a constant that you have to calculate the ratio. The name of the ratio is beta. Okay, so beta is the ratio between ZC and PC. Okay, by common sense, if ZC is less than PC, so meaning that the ratio of ZC over PC must less than 1. Okay, must less than 1. Therefore, beta is less than 1, right? So similar to the lag compensator, okay, uh, lead compensation also have their own board diagram. Okay, the board plot for the lead compensator. Okay, so the The first one is the magnitude, okay? The magnitude of S plus ZC plus 1, which is this one, okay? Okay, so that one is represent the ZC, okay? 1 over ZC plus 1, which is the break frequency at ZC. And the second one is the combination of the PC, 1 over PC plus 1, okay? Where the break frequency is at PC. So when you add together between this ZC and this PC, it will give you the bold line there, okay? The bold line is the total between the ZC and PC. This is for the magnitude in decibel. For the phase, also the same, okay? This is the phase where 1 over, where the ZC is over here, okay? The ZC is over here, okay? And the PC is over here, okay? So PC, okay? So therefore, the combination, the total between the ZC and PC will give you the bold line. This is for the phase boat load for the lead compensator. So what actually lead compensation do? Okay, so it's based on the graph on the right and the explanation on the left. So the uncompensated system, okay, before design, the uncompensated system has a small phase margin, okay, small phase margin and a low phase margin frequency, okay. Phase margin frequency is the omega Pn, okay, very low, right? So by using a lead compensator, so the gain crossover frequency is increased. The gain crossover frequency is increased from A to C. Yeah, from A to C. So we bring the magnitude curve shift up a little bit, okay? Omega Gm, okay? So the impact is a larger phase margin, okay? A higher phase margin frequency, C, and a larger bandwidth. So the impact is 3. One is you have a large phase margin. The second one is you have a higher phase margin frequency and a larger bandwidth. Okay, the closed loop, omega 3 dB, omega 3 dB. So it described by the graphics on my right, okay? So this, we have a 3 graph in the magnitude curve over here, okay? One is the compensator, sorry, one is the uncompensated, okay, before design. Then you have the compensator. So the compensator will compensate the uncompensated system, and then it produces the compensated system, okay? So there is a difference between uncompensated and compensated. Uncompensated is before design. Compensated system is after design. Compensator is the tools, the lead compensator that will compensate uncompensated system become compensated system. So it happens to the phase degrees as well, okay? It happens to the phase degrees as well here, okay? Where you have the uncompensated system, okay? Uncompensated system. And this uncompensated system will be compensated by the compensator. And this the compensator will produce this compensated system. So the boat load for the lead compensator, since beta is less than 1, okay, so the standard form for the magnitude curve is shown here. Start from beta 0.1, beta till 0.5. So we know that beta is the ratio between the ZC and PC, and it must less than 1, okay? And similarly, go to the phase. Okay, this is the phase, and the magnitude. Okay, so you can see the variations. Okay, the variations between the beta 0.5 and beta 0.1, right? So the peak and phase curve is vary, okay, in maximum angle at the frequency where the maximum occurs, right? So for lead compensation, excuse me, so the frequency at the maximum phase angle, okay, frequency at the maximum phase angle is given by equation 1, which is omega max equal to ZC divided by square root beta, okay? So beta is ZC over PC. And then the maximum phase angle, okay, the maximum phase angle, okay, is given by phi max, okay, phi max equal to inverse sine 1 minus beta divide 1 plus beta, okay, inverse sine. That is equation number 2. Then the compensator magnitude, which is omega max, okay, compensator magnitude, okay, at omega max, okay, here omega max is the magnitude, okay, magnitude GC, J omega max equal to 1 over beta, okay, so beta is the ratio between ZC and PC, and beta must less than 1. As I told you before, steps is matters in compensator design, right? So there is a step designs for lead compensator. Okay. So the first one is to obtain the value for K, which satisfy the steady state error, and plot the corresponding workload, right? Of course, workload is given, okay, it's given. So the second one is to find the phase margin of the uncompensated system, okay, phase margin before design, okay. Number 3 is to calculate the additional phase needed, okay, by the lead compensator so that it satisfies the system requirement, okay. So we might need additional correction factor, okay, might be needed. That is plus 10 degree, okay, correction factor. That is number 3. Number 4 is you have to calculate the beta. Okay, so beta is ZC over PC. Find the ZC, excuse me, find the ZC and find the PC. ZC and PC is the break frequency. Okay. Continue. Number 5, step to design for lead compensator. Then you have to calculate the compensator magnitude, okay, to obtain beta, okay, the magnitude, the J omega max, okay. Okay, that's step number 5. Step number 6 is you have to obtain the new gain crossover frequency, omega new gain crossover frequency, omega G, omega GM, subject to the magnitude of uncompensated system is equal but negative to that of the compensator. Hence, it calculates for the ZC and PC. Okay. And the final one is to draw the workload, and check the system performance. Is it fulfill the spec design? Okay, repeat the design step with different correction factor. Okay, if the system requirement is still not achieved. Okay, that is number 7. We go to example 5. So example 5 is similar to example 1, okay, and example 3, okay, is similar, okay. In the gain adjustment also use the same examples. Lag compensator also use the same examples, okay. And lead compensator also use the same examples, where you have a motor system, okay, with the input is desired position and the output is shaft positions. So usually the desired position is in radian, okay, and the output also in radian, okay. And there is a preamplifier, there is a power amplifier, there is a motor and load, and there is a 1/S, okay. So you are required to design lead compensator, okay, and to achieve 20% overshoot, and to achieve KV40. KV is velocity error constant, okay, with a peak time TP 0.1 second, okay. So this KV is related to the steady state error, where ESS is equal to 1 over KV, okay, 1 over KV, right? And the KV also have a formula, limit S to 0, okay, S K ds, okay. That is the formula for KV, okay. And error is 1 over KV. And this open loop transfer functions is 100K, okay. K multiply 100 multiply by 1 multiply by 1 and over S plus 36 and S plus 100. This is the way you analyze the problem, okay. Read the question, try to understand, try to relate the basic formula that we learned, okay, in the previous chapter, right? So, and we have 3 targets to fulfill, which is the overshoot 20%. So we can imagine that overshoot will give zeta. Zeta will give phase margin. So that kind of relationship you must try to relate in order to understand the problem, okay? And this system have KV equal to 40, meaning that this system is a system type 1. Is a type 1, okay? Because you have S over here. You have a S over here, right? Right. So as I told you before, KV is equal to 40, which will give you the gain of the system at 1440. Okay, how you get this? Okay, the workout is over here, is down over here. Okay, KV is equal to limit SGS. Okay, where limit S 100K. This is the open loop transfer function. Okay, open loop transfer function. Okay, so when you replace S equal to 0 inside, so it will give you, okay, KV, which is equal to 40, okay, 100K, the numerator, S cancel out, okay, so the remaining will become 36 multiply 100, okay, so therefore K is equal to, this one can cancel out, this one can cancel out, so 36 multiply 40, so you will get K1440, okay? Okay. So then we plot the board diagram with K1440, right? then we know that desired 20% will produce a zeta. Okay, zeta. Okay, so what is the zeta value? The zeta value we can get from the formula. Okay, overshoot formula zeta, or simply using the graph, standard graph. Okay, so 48.1 is about 50, is somewhere here. Okay, so the zeta value is roughly about 0.4, 0.5, roughly. Okay, then the open loop transfer function is given by 100k s cubic plus 136 s square plus 3600 s. Okay, and the phase margin over there. So you will get a formula, or you can use the graph, or you can use a formula. Either one will do. Okay, the zeta is 0.456. That's fine. Okay, 0.5. All right. And it will produce you 48 degrees. So just take a round up, 48 degrees, because 0.2 we cannot see in the boatload. So this is the empty boatload. Okay, I just plot it using Excel. If you have a printer at home, so you can use your printer and print this slide, or simply if you have a Acrobat reader, okay, you can, you can jot down like what I did just now. Okay, this is 0 decibel. Okay, so you can edit the PDF. Okay, and this is the slope is minus 20 dB per decade. Okay, and similar to the phase as well. Okay, if you look at the phase here, this one is minus 150. Okay, sorry. So this is minus 150. This is 200. Okay. So the range is 50 degrees. Am I right? And the segment is 1, 2, 3, 4, 5. 5. So meaning that one segment is equal to 10 degrees. Okay. So 150, 160, 170, 180. So 180 is somewhere here. Sorry if my line is not straight. Okay. So you can play around with the empty booklet. But to save our time or during online lecture, so we just using MATLAB. Okay. So this one is 1440. You know already how to calculate this. Okay, is a key, right? Multiply by 100, then you get this final open loop transfer function and plot using MATLAB. Okay, so if plot using MATLAB, you can see that the phase margin before compensated is 34 degrees, and gain margin before compensation is 10.6 decibel. Okay, right. So from the booklet, okay, is phase margin is 34 degrees at 29.6 radian per second. Okay, 29.6. Okay, omega. They want omega phase margin 29.6 radian. This one omega. Sorry. Omega GM is 60 radian per second. Okay, radian per second. Okay, phase margin 34 degrees at 29.6 radian per second. Therefore, the required phase margin from the lead compensator is 48 degrees. Okay, 48 minus 34. Okay, minus 34 from the open loop transfer function plus 10. Plus 10, and which is equal to 24.1. Okay, roughly 24 degrees. And 24 degrees, it occurred at 37.1 radian per second. Okay, 37.1 radian per second, somewhere here. Okay, somewhere here, 37.1, which will give you the phase margin roughly about 24.1 degrees. Okay. Right. So we use the formula, the three formula for the lead compensator, which is omega max, P max, and the magnitude of at frequency maximum. First is you calculate the beta. Okay, you calculate the beta, which is 24 degrees. Okay, that we get previously. Then find beta. Okay, so find beta. So you solve this. Okay, so beta is equal to 0.42, less than 1. Okay, then after that, after you get the beta, you calculate the omega max. Okay, omega max, which is ZC. Omega max is the frequency. Okay, the frequency which occurred is 39.6 radian per second multiplied by beta. So you get ZC. So ZC is the 1 over 25.66 plus 1. You already obtained ZC. After that, you calculate the magnitude. Okay, the magnitude is 1 over square root beta, which is 1.543. So it occurred at 3.76 decibel. Okay. So using the equation, P max at 24 degrees, beta at 0.42. So the lead compensator magnitude is 3.76 decibel. Okay. And to select a new phase margin frequency, find the frequency maximum at the compensator magnitude 3.76 decibels. And then from there, you get the maximum at 39 radian per second. Okay. So therefore, you get ZC. After you get ZC, you use the beta, you will get PC. Okay. Then PC is 60.2 and 25.3. And this value will go inside here. Okay. So the origin is 1 over 25.3 plus 1 divided by 1 over 60.2 plus 1. So you simplify this. Okay. You simplify this, then you will get the 2.38. 2.38 is actually 60.2 divided by 25.3 is the ratio. That's why you get 2.38. And the final compensation transfer function is GC. Okay, 342,600 S plus 25.3 S plus 36 S plus 100 and S plus 60.2. Okay, then you plot. Okay, then you plot. You can see that it achieved at 45 degrees phase margin. 45 degrees phase margin. Okay, so this is the target design. Okay, 39 radian. Right. Okay. So it's a long lecture for lead compensator. So now I open questions to everybody. Time remaining about 6 minutes. Is there any question you want to ask on the lead compensator? Zulaika, any question?
No, sir.
Zulaika Muhammad.
No, sir.
No, if you no question, I will ask you questions. What is the difference between lead compensator and lag compensator? Give me two differences between lead and lag compensator. Zulaika Muhammad.
Angle, sir.
Huh? Angle.
Frequency.
Frequency, kata betul ya. Saya tanya Asrul Hafiz. Asrul Hafiz.
Nilai beta tu.
Nilai beta. Macam tak tepat. Apa beza lead dengan lag compensator? Tak tepat tu. Azi Alia. Test kehadiran. Apa beza the difference between lead compensator and lag compensator? Give two difference. First one is Azi Alia. Tak datang.
Ada.
Dia. Apa dia? Beza dia ialah the difference is lead compensator is to improve transient response. And lag compensator is to improve steady state error. That is the first one. The second one? Kita tanya Ong. Mr. Ong, can you give me an Ong answer? The second difference between lead and lag compensator. Mr. Ong, hello? Ong tak ada. Syaza Yunus. Syaza Yunus. Hello? Syaza Yunus. Tak datang. Tak datang. Okey. Apa dia ni? Zulhairi. The second difference is the ZC and PC value. For lead compensator, ZC is less than PC. For lag compensator, ZC is greater than PC. What is ZC and PC? ZC and PC is the value of the break frequency of the compensator. Okay, so itu adalah two difference. Okay, between lead and lag compensator. Okay, any question? Time remaining 2 minutes. So after this, we will go for the second example.
Sir, saya terlepas dengar tadi sir.
The first difference is lead compensator.
Pasal ZC yang PC tadi.
Oh, ZC dengan PC.
Nah, tadi saya ada cakap kan sebelum
Lead compensator, for lead compensator, ZC is less than PC.
Okay.
Okay, so saya pakai whiteboard lah, senang. Show me. Okay. Okay. Lead ZC less than PC. Lag COM.
Okay.
COM tu bukan komputer, COM tu adalah compensator.
Okay.
Nampak beza dia? Lead adalah to improve transient.
Lead improve tension.
Faster lah. Faster.
Okay.
On. Lag to improve steady state. Okay. Nampak? Oh, tak share.
Nampak tu?
Nampak. Okay. So, ada apa soalan lagi? Selepas ini, I will show examples, another examples for lead compensator, and then some lag compensator. Okay, and then part 3, I will go to the past year test 3, the test 1, past year test 1. Okay, so we will go to the 18, 19, 17, 18, 16, 17. Okay, so I stop here. Okay, then I see you in the second part. So rest for 15 minutes. Rehat 15 minit.